Good afternoon. My name is Nitesh Bhatia, and I work at Imperial College London. The title of my talk is Visualizing Time-Varying Complex CFD Flows in Virtual Reality. The talk covers our recent work on visualizing transient CFD flows in virtual reality. In past years, our research group led by Professor Omar Matar has been exploring creative approaches of teaching and visualizing complex fluid dynamics data. We are actively using virtual, augmented, and mixed reality approaches in classroom teaching. A transient flow is a type of flow when fluid is unsteady. The flow parameters such as velocity and pressure are dependent on 3D position as well as time. Our aim is to design a PCVR system where a transient flow can be visualized in an interactive manner. In this work, we have visualized transient flow parameters that are limited to vector fields such as velocity and 3D objects such as interfaces and surface geometries. With this approach, we are able to visualize simple as well as complex industrial transient flows such as mixing, turbulence, stirring, and bubbles. So what is virtual reality? It is a computer-generated immersive data visualization technology where a user can naturally experience autonomy, interaction, and presence. The user can react to events and stimuli, interact and control the data around it, and achieve total immersion through sensory input. Hence, in the context of education, our motivation is to utilize virtual reality such that students gain an intuitive understanding of time-varying flow characteristics derived from in-house CFD simulations of complex industrial processes such as mixing in stirred vessels. A typical PCVR system consists of hardware such as Oculus Rift or HTC Vive connected to a PC running VR software. The hardware includes a VR headset that simulates visual sense and hearing to a user, as well as changes in the VR viewport with respect to user's point of view. It also includes controllers for simulating hand movements, interaction, and user interface inputs via buttons and triggers. The PC does all the heavy lifting of rendering the viewport and processing commands. It is handled by VR software. Unity is one such software which is pretty much current industry standard. It is a programmable virtual reality software that supports languages such as C#, C++, Mono, .NET, and Python. It also supports a lot of plugins. For this work, we have leveraged Visual Effect Graph. It is a plugin that renders millions of particles using GPU. The particle velocity component can be confined to any 3D vector field data. In our case, we have taken flow velocity of CFD data as one of the vector field. We have also used Unity XR plugin for UI control and input. Coming to the data processing methodology, the first step is to generate the CFD data. It involves mathematics, experimentation, simulations, and tools such as OpenFOAM, CodeBlue, and ParaView. The second step is to post-process CFD data to VTI format, which is a platform-neutral format. Vector fields are stored as VTI files, and interfaces are stored as OBJs. We have utilized tools such as VTK and PVPython. The third step involves translation of VTI data to Unity native format, such as 3D texture or vector fields. For this, we have used custom C++ Qt codes. The last step is to visualize the data in Unity VR. We have used visual effects graph in GPU for rendering millions of particles and XR input for user interface control. So what you see is an immersive flow that varies over time, which is visualized as 3D flowlines surrounding the surface of a 3D model. The flowlines consist of thousands of particles rendered with GPU. The particles are programmed in such a way that they orient and follow the direction of 3D vector field data, that is the velocity in current case. They appear in different hues of color representing scalar magnitudes of 3D vector field. In this talk, I am showing you two example implementations. The first one is a rising bubble. The left-hand side shows the time-varying CFD data visualized in ParaView at 3 frames per second. The streamlines follow velocity vector and color represents its magnitude. The right-hand side is what a student sees in VR. There is a control panel user interface where the time-varying data can be viewed frame-wise or as a sequence at 1 frame per second. By moving closer, one can immerse into the data in 360 degrees. The second example consists of a rotating impeller, which is an industrial use case. There is a separate talk in APS-DFD 2020 this year by Lyes explaining the fluid dynamics behind a rotating impeller. The left-hand side shows the rotating impeller in paraview. Note the change in the interface and bubble formation as the air starts to mix into the fluid. The right-hand side shows the VR visualization. The red color represents high magnitude and the blue color represents the lower magnitude. Concluding this talk, in this work we have presented our approach for immersive visualization and exploration of large CFD flows of time-varying vector fields in virtual reality environment. Processing and visualization of large CFD datasets can be expensive in terms of computation and rendering time, especially for VR scenarios. Hence, in our approach, we have utilized a consumer-grade GPU for interactive visualization of time-varying three-dimensional vector fields such as velocity. The immersive system is built using Unity virtual reality development software and is capable of complex industrial CFD visualizations. I hope you enjoyed the talk. Thanks a lot for your attention.